Hi guys, today is March 30th, and today what we're going to be learning is radius of convergence day 2. Okay, we're just going to jump right into the examples. All right. Okay, so um, one quick little thing I need to do is I needed to make there's a correction on the problem here. Okay, so find the interval of convergence, and within the interval, the sum of the series as a function of x. Okay, so here's the problem. I need to switch this from n equals 1 to n equals 0. Okay, all right, and I'm going to need to do that on part B too. So if I forget to say something, okay, I'll do my best and say, hey, we need to switch it on part B too. Okay, um, actually, let's just go ahead and do it. So down here in part B, let's just switch this to n equals 0. Okay, all right, so back to this. All right, so we want to find the interval of convergence. So what you have to notice is that this is a geometric series. Okay, so this series right here is a geometric series, and I'm going to capitalize it. I guess you wouldn't have to. Geometric series with r equal to, and okay, so if we put 0 in here, it'd be sine x over 2 to the 0, and then we'd put 1 in, and so we're multiplying by sine x over 2, right? So that's our r, would be sine of x over 2, and it converges when the absolute value of r, which is the absolute value of sine of x over 2, is less than 1. Okay, all right, so this translates into, okay, -1 is less than sine x over 2, which is less than 1. Okay, and then multiplying the left, the middle, and the right by 2, we get -2 is less than sine of x, which is less than 2. Okay, so this works. Okay, so this is going to, and we could go ahead and come up with our sum here. Okay, or our function that represents the sum. Okay, um, and the interval of convergence would be whenever sine of x is between -2 and 2. Well, what do we know about sine x? Sine x is always in between -1 and 1, including both -1 and 1. So sine x must always be between -2 and 2. So for any x, this is going to be true. Okay, so let's write this. Okay, so sine of x is between -1 and 1. And you wouldn't have to write this. This is just our thought that's going on. Okay, between -1 and 1, including, okay, comma. Okay, so including means it can be -1 and it can be 1. All right, so sine x must always be between -2 and 2. Okay, so this is always going to be true. Well, what does that mean in terms of the interval of convergence? Well, if any x is going to, if any x we put into this is going to cause it to be between -2 and 2, that means this is going to work for every single x. So the interval of convergence would be -infinity to positive infinity. So there's no like distinct interval here. Okay, so the interval of convergence is -infinity to positive infinity. So the radius of convergence would therefore be infinity. Okay, and then the other part of this was the sum of the series as a function of x. Okay, so the sum, we use s for sum. Okay, it would be 1 over Okay, now why 1? Okay, now this, since it's a geometric series, there's a formula for the sum, right? So it's going to be 1 over 1 because the first term is 1. Because if we put 0 in here, that's why we need this to be 0. If we put 0 in here, okay, that'd be sine of x over 2 to the 0, which is 1, okay? Over 1 minus our r, which is sine of x over 2. Okay, so you really probably don't want to leave our answer like this, okay, because it's a complex fraction. So let's multiply the numerator and denominator both by 2. So a better sum would be 2 over, and then if we distribute the 2 here, we'd have 2 minus sine x. Okay, so what does all this mean? Okay, so here's this function, right? And here's a series that represents this function. And if we go to infinity, these are exactly the same thing. Okay, so here's the function, here's the sum, or the series rather, not sum. Okay, all right. All right, so let's go and let's do the next problem. Okay. Okay, so for example 1, part B, okay, here's our series, n equals 0 to infinity, natural log of x to the n. This is also a geometric series. So we'd say is a geometric series. And you would need to say this for the AP exam, okay? Is a that this is a geometric series with r equal to the natural log of x and converges when the absolute value of the natural log of x, because that's our r, is less than 1, okay? This would mean that -1 is less than the natural log of x, which is less than 1, okay? And now what we're going to do is we're going to exponentiate this, okay? Okay, so we're going to exponentiate the left side, the middle, and the right. So this becomes e to the -1 is less than e to the ln of x is less than e to the first power, okay? All right, so that means this becomes 1 over e is less than x, which is less than e. So that's our interval of convergence, okay? So the interval of convergence is parenthesis 1 over e, comma, e. Okay, that's the interval of convergence. What's the sum? Okay, so the sum would be our first term. So if we put 0 in here, natural log of x to the 0 would be 1. Okay, so 1 over 1 minus our r, and our r is simply the natural log of x. Okay, so what does this mean? This means that this function, 1 over 1 minus natural log of x, is exactly the same as the series starting at n equals 0 to infinity, natural log of x to the n. Okay, they are exactly the same, but not for all x's. Not for all x's. They're only the same for x's between 1 over e and e. Only those x's that this series and this function will be the same. Okay. All right. So this is a big deal. You can write a function as a series. Okay. All right. So let's go to the next example. Okay, for this next example, example 2, and it's part A, part B, part C, and part D, I believe, okay? We want to be able to determine the convergence or divergence of the series and then identify the test you use, okay? So we have the ratio test, we have the limit comparison test, we have the direct comparison test, we have the nth term divergence test, and we have some more tests that we're going to learn, and we're going to use those for endpoint, okay? For determine if the endpoint it's converging at the endpoint or not. All right. So right here, if you look at this, okay, and there's not a typo on this one, okay, but if we look sigma n equals 1 to infinity, 2 to the n over n plus 1, okay. So you're looking at this, okay, and it's a ratio of 2 to the n over n plus 1, and you should be thinking, okay, 2 to the n, that's going to grow faster than n plus 1, right? So I'm thinking to use the nth divergence or the nth term test to show that this thing diverges, okay? So what we want to do is look and see what is the limit as n goes to infinity of a sub n, right? So that would be the limit as n goes to infinity of 2 to the n over n plus 1, okay? So this is going to grow faster than n, so that means this is just going to get bigger and bigger and bigger, which means this is infinity, right? Okay, and now what has to happen is um, if this doesn't go to zero, then automatically we know it diverges. Now, this can still go to zero and still diverge though, or and still converge. Okay, we don't know. All right, but we do know that if this does not equal zero, then for sure it diverges. So since the limit as n goes to an infinity of 2 to the n over n plus 1 does not equal 0, right? Because it has to equal 0, or it has to not equal 0 for to know that the series diverges. Okay, therefore, this series sigma n equals 1 to infinity 2 to the n over n plus 1 diverges by the nth term test. Now, there's another way of looking at this, okay? Some of you might have been thinking, oh, the ratio test, right? And you could use the ratio test and you wouldn't be wrong, okay? Because if that ratio test, if you did the limit as n goes to infinity of a sub absolute value of a sub n plus 1 over n plus 1, you would have got a number that's bigger than 1. And if it's bigger than 1, that tells you the series diverges, okay? And that's what would have happened here too. You would have come out with a number that's bigger than 1, or it doesn't exist, which means it's infinity, okay? All right, so that would be an alternative. You would not be wrong. You would not be wrong if you did the ratio test on this one and showed it diverged that way, okay? I just think the nth term test is a little bit easier and a little bit quicker, okay, in this case. All right, let's go to the next example. All right, for this next example, it's sigma n equals 0 to infinity of n to the 10th power over 10 to the n, okay? And for this one, I'm going to look at the ratio test, okay? Why am I looking at the ratio test? One, because it's 10 to the n power, okay? So when you have an nth power, okay, or you have some type of factorial, you should be thinking, maybe use the ratio test, okay? So let's take a look at this. The limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, okay? And that would equal the limit as n goes to infinity, okay? And here's my main fraction bar, right? And it's going to be n plus 1 to the 10th over 10 raised to the n plus 1 power. You wouldn't really have to have the parentheses around this, okay? And then over the a sub n term, right? So that would be n to the 10th over 10 to the n power, close the absolute value, okay? Now, another way to write this is we're taking this fraction and dividing by this fraction, so we could take this numerator fraction and multiply by the reciprocal of this, okay? So this would be equivalent to the limit as n goes to infinity of the absolute value of n plus 1 to the 10th over 10 to the n plus 1 power times, okay, so if I do the reciprocal of this, it'd be 10 to the nth for the numerator over n to the 10th power, right? All right, rearranging this so we get like bases together, okay? This would be equivalent to the limit as n goes to infinity of the absolute value of n plus 1 to the 10th power over n to the 10th times 10 to the nth over 10 to the n plus 1 power. Close the absolute value. Okay. Now, this becomes 10 to the nth, and then 10, using exponent rules, this is 10 to the nth minus n plus 1. So that'd be 10 to the negative 1, or 1 over 10. Okay. So this is equivalent to the limit as n goes to infinity of n plus 1 to the 10th. Nothing we can really do to simplify this one, okay? Over n to the 10th times, and this becomes 10 to the negative 1, or 1 over 10. Okay, so now this one's not going to need the absolute value anymore, okay? And really neither is this one, right? So if we take the limit, and we can kind of do this all at once, take the limit and everything else together at the same time. All right, what happens when we take the n goes to infinity? Okay, well, it's the highest power, right? The highest power for this one's going to be n to the 10th, and this is n to the 10th. So as n goes to infinity, this is just going to become 1 times 1/10. All right, so it becomes 1 times 1/10, which is equivalent to 1/10. Okay, so what does that tell us? This limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, okay, is equal to 1/10. That's less than 1. Well, when using the ratio test, if that limit comes out to be less than 1, then we know the series converges, okay? And it's going to converge for all x values, okay? And really, even this problem doesn't have any x values, okay? Okay, so since, okay, the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1, right? So because it's 1/10, it's less than 1. The series sigma n equals 0 to infinity n to the 10th over 10 to the n converges by the ratio test. Okay, and that's example 2b. All right. All right, so looking at this next series, okay, n equals 1 to infinity of n times sine of 1 over n, okay? If you think about these terms, okay, they keep getting bigger and bigger and bigger and bigger, right? All right. If n keeps getting bigger and bigger and bigger, this 1 over n is going to get closer and closer to 0, and this is going to be sine of 0, but n is going to go to infinity, right? Okay, so what that means is as you go across, okay, as the terms, as you start writing the series out, the terms are getting bigger and bigger and bigger and bigger and bigger, which should make you think this sucker is going to diverge. Okay, so what we should be thinking in our head is the nth term test. Okay, all right, so what happens if we take the limit as n goes to infinity, right? Okay, so what happens is if we take the limit as n goes to infinity of n times sine of 1 over n, I'm going to think that this doesn't, that should be a parenthesis, not an absolute value. I'm thinking this should come out to be a number that's not equal to 0, okay? All right. So, because this is going to be like infinity times and 0. Okay. So we should be thinking maybe L'Hopital's rule. Okay. Now, we can't use L'Hopital's yet because L'Hopital's rule has to be a quotient, right? But we could write this as a quotient as long as we multiply this by 1 over n and divide also by 1 over n. So we're going to multiply by 1 over n over 1 over n. Okay. And so that's going to look like this. This would be the limit as n goes to infinity. If I multiply this by 1 over n and also divide by 1 over n, that becomes sine of 1 over n over, and what we have underneath here is a 1. So 1 over 1 times 1 over n would be 1 over n, right? Okay. All right. So now what happens on this? Well, what happens as n goes to infinity? Well, this gets closer and closer to 0, right? What's sine of 0? Well, that's be 0, right? And what does the denominator do? Well, this goes to 0, right? So we have the situation where, and we would need to write this to use L'Hopital's, is we have the limit as n goes to infinity of sine of 1 over n, and that would equal 0. And the limit as n goes to infinity of 1 over n is also equal to 0. So we have 0 over 0, that situation, right? So L'Hopital's rule says, okay, let's take the derivative of the sine of 1 over n. Now, remember, 1 over n is really n to the negative 1, okay? So this becomes the limit as n goes to infinity of, okay, so the derivative of sine of 1 over n would be cosine of 1 over n times the derivative of 1 over n. Now, 1 over n is really n to the negative 1. So that would be negative 1 n to the negative 2 over, okay, and we also have to take the derivative of 1 over n here. Well, that's n to the negative 1, right? And the derivative of this would also be negative 1 n to the negative 2, right? Okay, the negative 1 into the negative 2, negative 1 times n to the negative 2 here, they would cancel. You would be left with the limit as n goes to infinity of cosine of 1 over n. Now, as n goes to infinity, this is going to be 1 over, well, 1 over a big number, right? And 1 over a big number is 0. And then cosine of 0 is 1. So this turns out to be 1. All right. Okay, so what does that mean? Okay, so back to this, we did the limit as n goes to infinity, right? And if it doesn't equal 0, which it doesn't, right, then we know it diverges by the nth term test, okay? So we can say since the limit as n goes to infinity of n times sine of 1 over n does not equal 0, right? Comma, the series sigma n equals 1 to infinity n sine of 1 over n diverges by the nth term test. Okay, and that's that example. Okay, let's go to example D. All right, for this next example, we have sigma n equals 1 to infinity of n plus 1 factorial over 2n plus 3 factorial, okay? Because you're dealing with factorials, automatically you should be thinking, ratio test, okay? So let's take a look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, okay? And then that would equal the limit as n goes to infinity, okay? And it would be, this is our main fraction bar, okay? And it would be n plus 1 plus 1. So n plus 1 plus 1 factorial over 2 times n plus 1 plus 3 factorial. And then the denominator is n plus 1 factorial over 2n plus 3 factorial, and then the absolute value of that. Okay, so this is equivalent to the limit as n goes to infinity of the absolute value of n plus 2 factorial over, this right here would be 2n plus 2 plus 3. So it'd be 2n plus 5 factorial times, now this one, remember we're going to multiply by the reciprocal of this fraction right here. Okay, so it's going to be 2n plus 3 factorial over n plus 1 factorial. And then close the absolute value. Okay, so this one is n plus 2 times, and then take 1 away, right? So that'd be n plus 1, and then on down, right? So what we're going to be left with when we look at these two is we're going to be left with n plus 2 in the numerator, okay? So this is going to equal the limit as n goes to infinity of the absolute value of n plus 2. Because remember, n plus 2 would be n plus 2 times n plus 1 times n minus 1 times n minus 2 times n minus 3 on down, right? And this one's n plus 1 times n minus 1 times n minus 2, and so on, right? You just keep taking 1 away, right? So a lot of, since this one's bigger, right, it's going to cancel a bunch of these, right? So we're going to be left with n plus 2. Okay, so n plus 2 in the numerator. Okay, so here in the denominator, this is 2n plus 5 factorial. This is 2n plus 3 factorial, right? So the first one is going to be 2n plus 5, right? We're going to have 2n plus 5. And then we're also going to have a 2n plus 4. But then 2n plus 3 on down is going to cancel with the 2n plus 3 factorial up here, right? So that's what we're left with, is that, okay? All right. And as n goes to infinity, the numerator, the power in the numerator that's controlling the growth is this n, right? Down here in the denominator, it'd come from 2n times 2n, right? And 2n times 2n is 4n squared. So we could calculate this limit by taking the limit as n goes to infinity of n over 4n squared, okay? And so we know that the denominator is going to wind up growing faster than the numerator in this one. So this is going to go and it's going to equal 0, okay? Now, that's less than 1, right? Since it's less than 1, then now we know that that's going to converge by the ratio test. So since the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1, we know the series sigma n equals 1 to infinity of n plus 1 factorial over 2n plus 3 factorial converges by the ratio test. And this is just, we're getting more and more practice of just using the different tests to determine whether a series is converging or divergent, okay? The only thing I know is just to give you guys a lot of practice, and there's more than one test you could use. I mean, you could use something else with this. Because of the factorial situation in this particular problem, I would definitely use the ratio test. So anytime you see factorial, ratio test, okay? You should be thinking that, all right? The other ones, there might be other ways to do it, but definitely ratio test on this one, okay? All right, let's look at the last problem. All right, for example 3, we want to find the sum of the telescoping series sigma n equals 1 to infinity 40n over 2n minus 1 squared over 2n plus 1 quantity squared, okay? All right, so you want to do some partial fraction decomposition on this. I'm not gonna take the time to do that because we've already done that several times, okay? But I'm gonna show you what this comes out to be, okay? So to set this up, we would do 40n over 2n minus 1 squared times 2n plus 1 squared, and that equals, some number a over 2n minus 1 squared, and then plus b over 2n plus 1 squared. Okay, and then we would work this out. Okay, if you work this out and figure, you multiply to clear out your denominators, right? And then you pick a value of n that would cause one of them to cancel and become 0, right? All right, when you do that, when you do this, you would wind up with a is equal to 5 and b is equal to -5. Okay, all right, so that's what would happen. Okay, so what does that mean? That means this series can be rewritten. Instead of writing it like this, we can write it like this. Okay, and so the series sigma n equals 1 to infinity 40n over 2n minus 1 squared times 2n plus 1 squared. Extend my fraction bar a little bit there. That would equal sigma n equals 1 to infinity of, okay, and my a is 5, so that would be 5 over 2n minus 1 squared. Now my b was negative, right? When we worked this out, we got b is -5, okay? Or when you worked it out, okay? So that makes this minus 5 over 2n plus 1 squared. I'm going to close my bracket here, okay? All right. Now, to find the sum, okay, for this telescope, remember some of these are going to cancel out, right? And we got to come up with a formula for S sub n, okay? So if we start looking at this, okay, what if we put 1 in? Or let's start taking a look and seeing what does this series give us, okay? So if we put 1 in, okay, we're going to get 5 over, okay, and this one would be, if we put 1 in, right, it'd be 2 minus 1, which is 1 squared. So it'd be 5 over 1 minus 5 over, okay, and we put 1 in here, right? So that'd be 2 plus 1, which is 3, and then squared is 9. So this is minus 5/9, right? And that would be the first term in this telescoping series, okay? And then we would add to that, and then we put 2 in, right? So if we put 2 in, it'd still be 5 over 2 times 2, which is 4. 4 minus 1 is 3. 3 squared is 9. So this one's 9 minus putting 2 into the second term right here, okay? So it'd be 2 times 2 is 4 plus 1 is 5. So that'd be 25. Okay, and then plus, okay, then we're going to put 3 in, right? And we put 3 in, it'd be 5 over 2 times 3, which, 2 times 3, which is 6, minus 1 is 5. 5 squared is 25. Okay, and then minus, and putting 5 in here, that'd be 5 over, that'd be 2 times 5, which, I'm not 2 times 5, 2 times 3, which is 6, plus 1 is 7. 7 squared is 49. Okay, plus dot, dot, dot. Okay, so the last, okay, the nth one, right? The nth one would be 5 over 2n minus 1 squared minus 5 over 2n, 2n minus 1 squared, 2n plus 1 squared, right? Close parenthesis, and then plus dot, dot, dot. I'm losing room right there. Okay, sorry guys. All right. Okay, so that's the nth one, right? But if you look at this, there's a pattern here, right? The second term in the second fraction in the first term, right, is going to cancel with the first fraction in the second term, and that's always going to happen, right? So what would happen is this one's always going to cancel with this one, right? and then these two are going to cancel, and these two are going to cancel. And so at the end, if we went S sub n, right, the sum of the nth term, okay, we would always have this first one, right, 5 over 1, right? And then what's going to happen is this one, this term right here, 5 over 2n minus 1 squared, will have canceled with the last one up for the term before it, right? Okay, so we're going to be left with minus 5 over 2n plus 1 squared. Okay, so that's a formula that will give me, like, if I want the 50th, what's the sum of the first 50 or the first 100 or the first 200? I could do that by putting 200 in for n. But that's not what's really happening, right? We're not stopping this at 200. We're going to go to infinity. So how do we actually find the sum? Okay, so what we have to do is we have to take the limit. I should write sum. Okay, let's write S for sum. Okay, so let me slide it up a little bit too. Okay, so S is equal to the limit as n goes to infinity of S sub n. Okay, and we did this, back in the last unit, okay, but I just want to reiterate this and just see, so you see it again and you get better at it every time you see it, okay? You get a little bit better each time, okay? So this would be the limit as n goes to infinity of 5 over 1, which is really just 5, minus 5 over 2n plus 1 squared, right? So this would be really what's causing this growth, right? Because we're n's going to infinity, is the 4n, this becomes 4n squared, right? And that's what's controlling the growth. And this is just 5, right? The numerator is just 5. So this denominator is just going to get bigger and bigger and bigger, which means this fraction is going to get closer and closer to 0. And so 5 minus 0 is just 5. So that's the sum of this telescoping series. It's going to be 5, okay? But you have to go to infinity for that to happen, right? Because that's what this is saying. N goes to infinity, right? You have to go to infinity for it to equal 5. All right? And that's how you find the sum of a telescoping series again, okay? All right, just a quick review for you guys. Partial fraction decomposition for this, right? And I just didn't show you the work involved in this. Oh, I'm pointing to this up here, right? Sorry. Okay, so we did that. I just kind of gave you the answer to what A and B would be, okay, because we've done that enough, I think. All right. Okay, guys, so that's the end of this lesson. Okay, I'm gonna pull up the calendar and show you this next assignment. Okay. Okay, guys, so we're on this assignment, radius of convergence, day 2. We're talking about interval of convergence, determining convergence and divergence, telescoping series. And I want you to do these problems. So it's assignment 11.6, and I want you to do page 515, 29 through 43 odd, and 49 through 53 odd, okay? And this is March 30th. Okay. And you guys, I know in all this craziness, we're still ahead, guys. We're still ahead of when I've done this in the past. Okay. So we're doing really good. Okay. Hang in there. Right now, I told my AB class on today's lesson that what I really want, we're supposed to come back May 4th. Okay. And then May 5th is our AP exam, right? The very next day. But really what I want us, I want to if at all possible, I want us to try to take the full-blown exam, okay? I just think it's better for us. Right now, they're saying there's not going to be an AB subscore, okay? If you take the BC test, you just get a BC. You're either going to pass it or not, and no AB credit at all, okay? That's what they're saying right now. Everything is changing, though, okay? All right. So I think it's just better if we actually take the full-blown exam. So I'm going to prepare you, and we'll have time. I'm going to prepare you as if we're going to take the full-blown exam. And then if we don't, we'll make adjustments. Okay. We just gotta be flexible. Okay. All right. So do this assignment. All right. Keep up with the work. It's not a big deal. I know some of you have emailed me or texted me and said, "Hey, Mr. Mitchell, I can't get this in by this time." That's absolutely fine. It's more important that you complete the assignments and do an honest job on them, not just copying the assignments, okay, from the solutions. I know you guys don't do that. All right. But just important that you just complete the assignment. Don't worry about the official due date, okay, or the due time or any of that. you guys, I'm going to go into Google Classroom and I'm going to give you the points. Okay. If you turn it in a day late, 2 days late, 3 days late, do not be concerned. Okay. All right. You're going to get full credit. Okay. All right. So you guys take care. And I will see you for the next lesson, guys. All right. Bye.